Hello everyone, welcome to the connecting position, velocity, and acceleration functions using integral notes. This is 6.11 for us, but technically it is in AP Classroom as 8.2. So this is just going to talk about, very obviously, how these things that we learned back in Unit 4 connect to what we're doing today. So just a recap, position is the position of a particle, right? And a lot of times we define it by an S of t, or a lot of times you'll see P of t. Velocity is the velocity. It's a vector, and so it's talking about how quick something is moving, right? An object is moving, but it also incorporates the vector part, the direction it's moving to. And so we defined velocity with a v of t, but what we learned in Unit 4 is that velocity is equivalent to the derivative. I'm going to use my s. It's equivalent to the derivative of position. So velocity is the derivative of position. And then acceleration is how quick the velocity is changing. And so how quick, not necessarily always how is it speeding up or slowing down, but how it's changing. And so we define that by a of t, and that is equivalent to the derivative of velocity and the double derivative of position. So derivative velocity of velocity, double derivative of position. So that's just recap of things we learned a couple months ago. And so how does that connect to integrals? So the connection to integrals is fairly obvious if you know what antiderivatives mean. So the antiderivative of acceleration is velocity. So just moving backwards. The antiderivative of velocity is position. And so you just move the opposite direction. And so here are some words that we are going to talk about a lot in this section. You see these words all the time. We have displacement of a particle, the total distance traveled by a particle, and then the final position of a particle. And so displacement of a particle is defined by the net change, or the net distance traveled by a particle. And a little example of this is, let's say that I go on a run, and then I start at my house and I finish at my house. My net distance over that run is 0 because I got back to my starting point. But let's say that I went on a run, I ran a mile north, and I stopped at Starbucks. So then my net distance is a mile because I'm a mile from home. But then again, if I went back home and I ran a mile north and a mile south, my net distance would be 0 because I'm back at home. And so that's the idea of net distance. And so the way that you find the net distance, the displacement of a particle, is the displacement of the particle is going to be the antiderivative of velocity. And if you guys remember, at the very beginning of Unit 6, we talked about how the integral is the language we use. The integral of a rate curve is the accumulation of something. And so, the velocity curve is a rate. A lot of times it's miles per hour, right? And so the integral of that is going to be the accumulation of the distance, but it's the net distance. It's not the total distance. And so that's why it's the antiderivative of velocity. Versus the total distance traveled by a particle, let's say we're going between A and B, right? The total distance, that does not include the net. So this concept is say I'm running to Starbucks. It's a mile from my house. I run a mile north and I run a mile south. My total distance is 2 miles. My net distance is 0, but my total distance is 2 miles. And so the way that you find that is you do the absolute value of velocity, because that will tell you the accumulation, but it will tell you the accumulation and not include the idea of the vector, which if you're moving left or right, those cancel each other out. But it's just what is it all together? So that's the absolute value. I'm going to draw a little sketch over here on the side to help us explain this. And then finally, the final position of a particle. So obviously we could use the position graph, but we're assuming that we don't have this. So the final position of a particle is going to be first this right here. So let's say this is the final position where you start at A and then you travel to B. Okay. So S of A here stands for our initial, the initial place the particle was, the initial position of particle. And then to figure out like where is the final position of the particle, what you would do is the velocity curve tells you the total distance the particle is from the starting, right? And so you would do the initial position plus your net distance, and that would tell you the final position of the particle. And so here's just like a little example. So let's say that v of t equals 4 minus t. So this is just going to be a little sketch. So this is our velocity curve, but it's going to be a straight line this time. So say we start at 4, and then we go down 1 over 1. Straightest line we can do for right now. Okay. So say it looks something like this, okay? So for the net distance, you would have, like, say we go all the way over here to 8, right? The net distance, like these two spaces, they cancel each other out. And so that's why that's the net distance, okay? So those two spaces cancel each other out. But like total distance, the way that you're thinking about this is you're thinking about this as the absolute value. So you're kind of imagining this happening to the curve. So you have these two sections, and this is the absolute value of this section, and so that will tell you the total distance that you actually traveled. So that's kind of just like the connection here. And then this section again right here, like if I don't go back to this, I'm talking about final position here, like this curve right here will tell you how much it traveled, but because it's the velocity curve, not the position, you have no idea where it started, and so that's why you need this S of A information. So that's just kind of like graphically what's going on here. But we're going to jump into a couple problems, and hopefully the more examples we do, the more clear these become. So our first problem right here says a particle moves along a straight line with acceleration modeled by A of t equals 4t. The velocity and position of the particle are modeled by v of t and s of t, respectively. Given that v of 0 equals -2 and s of 3 equals 0, determine s of 6. So our end goal is to figure out the position at 6. That's what this means right here. And we're given acceleration, and then we're also given these two pieces of information. So what does v of 0 equal -2 mean? That means that's our initial velocity because it's 0. And then this is just the position at 3. So we got to get all the way to the position function, and we are starting with the acceleration function. So the way that this helps us out is that we know the acceleration, the antiderivative of the acceleration is equal to the velocity. And so I'm going to start by taking the antiderivative of acceleration. So I have 4t dt. The antiderivative of that is 4t squared over 2, and then remember plus c. And so that is our velocity function in a sense, but we need to figure out, to continue on, I'm going to simplify this, we do need to figure out what is c. Well, we're told if we plug in 0, we'll get out a -2. So let's just imagine this. If I plug in 0, I should be getting out -2. So this right here cancels out, so I'll get c equals -2. And so that means that my velocity function is 2t squared minus 2. And so anytime it's an initial, you can just go ahead and plug it in for c. And a lot of people got this question correct on our last test. It was an extra credit question. So now we know the velocity, but our end goal is to find the position. So same idea, the integral of the velocity function is the position function. So I'm going to go ahead and take the antiderivative of this, and that is going to equal 2t cubed over 3 minus 2t plus c. And so that's what we have for our position, but I need the position function, which means I need to know what c is. I'm told if I plug in 3, I'll get out 0. So I'm going to plug in 3 here, and I should be getting out 0. So 2 times 3 cubed over 3 minus 2 times 3 plus c. This is 27 divided by 3. So it takes us back to 9, and then 2 times 9 is 18. 2 times 3 is 6 plus c. I'm getting 0 equals 12 plus c, so -12 equals c. So this is then our position function. Our position function is 2, I know we're running out of space here. But our position function is 2t cubed over 3 minus 2t minus 12. But the final question didn't ask us to find the position function, it asked us to find the position at 6. So we're still going, I'm going to plug in 6 here, and I'll get 6 cubed over 3 minus 2 times 6 minus 12. And that's going to end up giving us 144 minus 12, which, or sorry, minus, I plugged in something wrong earlier, hold on. Minus 12, which is 144. So that's, sorry, things are not working in my head right now. Okay, which is 120. So our end position is 120. Okay, next problem. This is going to be more of just like verbal representation. So this one says a particle moves along the x-axis. So at the time t, its position is given by s of t and the velocity is given by v of t. State the verbal statements that go with the following integral expressions. So I have 3 expressions. So this one, you might notice the bounds are 1a, bounds are 1a. This one has bounds of 1a too. This has an absolute value. This is just like a regular function, and this has this s of 1. So let's just go through this. Based on the fact that this is an absolute value, this is going to be the total distance, and feel free to try these on your own, but this is the total distance traveled by particle between 1 and 8 seconds. So that one's the total distance because it's the absolute value. So it's not, if it's the absolute value, it's not taking the idea that like moving to the left would cancel out the moving to the right distance. This next one is the change in, like, it's the net change, right? It's the net distance. And so it's essentially like our change in position completely. So it's the change in position between 1 and 8 seconds. And then the last one is going to be, so this part right here we know stands for change in position, right? And then this part right here stands for the initial position. So this is going to be not just the change in the position, but the position altogether of the particle. And because our upper bound is an 8, this tells us the change in position from 1 to 8. This tells us our initial. So this is going to be the position of the particle at t equals 8. So that's just kind of what these mean, a little bit more practice. We'll do a couple more examples. So example 3 says the particle moves along the x-axis. The velocity of the particle at time t is 8t minus 2t. What is the total distance? So total distance traveled by the particle at t equals 0 to t equals 4. So remember, total distance has to do with the absolute value of the velocity. That's what we just talked about. And so if we want to figure out the total distance, we're going to have to do the absolute value of the velocity, and then these are going to be our bounds. And luckily, we are given the velocity. And so on the AP test, like even if you don't know how to evaluate this integral, if you were to set up this function just like this, you would get a point, because that means like you understand how the integral connects to this problem. And then specifically, we want this. And so the question is like, what do we do with this absolute value? Because there is not an antiderivative rule for the absolute value. But if you were to imagine this graph, and I can go graph it in Desmos for you real quick. Desmos. Okay, let's go to Desmos real quick. So this graph, we are just going from 0 to 4. That's the only section that we're concerned about. And we're going to be graphing 8t minus t squared. And I have to use x's for this. But if you guys notice, from 0 to 4, this graph is positive. And so the absolute value part of this section doesn't really impact it. It's not the absolute value of like each piece of the function. It's the absolute value of the function as to get all together. And so because that graph is always positive, it doesn't really matter in this case. Like that, you don't have to keep the absolute value in mind. Like it doesn't actually matter here. So I'm just going to kind of get rid of it. I would need to use that if part of the function between 0 and 4 went below the x-axis. But from here, I'm just going to evaluate. So I'll get 8t squared over 2 minus t cubed over 3. And then I'm evaluating from 4 to 0 to figure out this answer. So then I'm plugging in. So real quick, 8 divided by 2 is 4. So when I plug this in, I'm going to do 4 times 4 squared minus 4 cubed over 3. And then if I plug in 0 there, it's just going to be 0. So I'm not concerned about that. 4 squared is 16. 16 times 4 is 64. 4 cubed is 64. So that's 64 over 3. If I want to do some nice fraction work, I'm going to, what is 3 times 64? 128. I think it's 256. I could be making that up, but I think it's 256. And then that equals 128 over 3. I'm going to real quick check all my math that I just did in my head, but I think we're correct. Oh, we're not. This is 192. My final answer is correct because I'm copying it off of my own work. But, okay, that part is correct. So the answer is 128/3. So that's the total distance traveled by the particle, which is probably equivalent to something like around 60 point something. So that's that one. Okay, one more problem. This says it's a calculator active problem, so we'll use the calculator for this one. So we'll go ahead and get started. It says a particle moves along the x-axis for 0 is less than or equal to t, which is less than or equal to 4. The velocity of the particle is given by v of t equals 2t sine t squared divided by 3, and the position is given by s of t. It is known that s of 0 equals -1. Find the position of the particle at t equals 3. So we're trying to find the like ending position. And so to find that, we have to keep in mind, okay, where did it start? And then how much did it travel? And so to set this up, to find this, what we're going to do is we'll do, to find the position at 3, we'll have to do the position, its starting position, right? And then plus all of the distance it's going to travel, the net change, which would be the integral of the velocity function. And technically, you guys do have the skills to solve this one using U substitution, but it's a calculator active problem, so you should use the calculator. Also, we're trying to figure out how much its position changed from 0 to 4, so that's why 0 to 4 goes here. And so I'm going to use the calculator to do this. I'm not going to waste my time trying to do this by hand. So real quick, s of 0 equals -1, it gives me that. And then I'm going to my calculator, so calculate 84 is what I'm using here. And I'm going to click math 9. And I'll put a 0 here, a 4 on top, and then I'll just plug in the function as it is. So it was 2, I have to use x, but it's 2x sine of x squared divided by 3, right? Yeah. And that equals, I should be getting something different out. So let me make sure I typed everything in right. Last time I got 5, Oh, sorry, one thing I changed, okay, going back to this real quick, it says, so it's telling us this function goes from 0 to 4, but it wants its final position at t equals 3, so I should be plugging in a 3 in here, not a 4, so change that real quick, that's why my answer's wrong, well, compared to what I did before, so let me fix this real quick. This top bound should be a 3, oh man, I cleared the whole thing, that's fine, we'll try again, okay, 0, 3, 2x sine x squared divided by 3. Yeah, and then I should get 5.969, so I'm going to round to 5.97 plus 5.97, and so our final answer and the positions, or the particle's final position is 4.97. We'll do one more. Hopefully this isn't too long. We'll see when I'm done. Okay, last one has 2 parts. It says for 0, which is less than or equal to 2, which is less than or equal to 6, a particle is moving along the x-axis. The particle's position, x of t, is not explicitly given. The velocity of the particle is given by v of t equals 2 sine e to the t divided by 4 plus 1. The acceleration, let's just say acceleration, of the particle is given by a of t equals that whole long thing. So this is, we're actually not going to use the acceleration function at all. This is like from an FRQ, and I didn't take every single part of it, but we can do everything else. So the total distance traveled by the particle from 0 to 6, so 0 to 6 are our bounds, because that's what we're concerned about, right? And then the total distance means we have to use the absolute value, because we have to not think about the net change. And then again, this is still a calculator active problem, so this one's going to be super easy. Really what they're testing in this problem is that you know that this connects to the antiderivative. And so even if you couldn't figure out anything from here, you would get a point for just setting it up just like this. But now I'm going to go to my calculator, because this is a calculator active problem, and I'm just going to plug it in. So my bounds are 0 to 6, and then this is the absolute value. If you want to get the absolute value, you go math, and then you scroll over to number, and then it says abs right there. So you'll do 2 sine of e, so second natural log e to the x divided by 4, and then this whole thing was plus 1. And so my answer is 12.57. So that's the total distance this particle traveled. And then finally, this last one, it says the particle changes directions exactly once. Find the position of the particle at that time. So this is, I know that we don't love this idea, but the particle changes directions when it switches from either, when the velocity switches from negative to positive or vice versa. Because If it's negative, it's moving to the left. If it's positive, it's moving to the right. So what we're going to do is we are going to plug in this function. We're plugging in the velocity function in for y equals. This is the best way to do it, unless you are really, really good at solving trig functions. So you'll plug the velocity function in here. And then we are only concerned, oh, hold on. Delete. We are only concerned about this function between 0 and 6. So I'm going to change my bounds, my x mins to be 0 and my x max to be a 6. And then I'm going to go to the graph. And this is what the graph looks like right here. And I'm concerned about where it's changing position. So if you guys look around 5, that's where it's changing position. I need to figure out exactly what it is. So I'm going to press second trace, and then I'll press my 0 button. And this is when we go left, and we press enter, and then we go right, and we press enter, almost there. We press enter, and we press enter, and it says 5.19. So the place where it's changing position is 5.19. And then it actually wants to find the position at that time. So to find the position at the time, well, we need to take blah, blah, blah. We need to take into consideration that its initial position, which is given us right here, its initial position is 2. And then from here over, I'll do 0 to 5.19, because that's how much it changes from 0 to 5.19. And then I'll just plug in the velocity function to figure out that net change. We need the net change because we're talking about like how close is it from the start, essentially. So then I will again go back to calculate 84. I'll press math 9. I'll go 0, 5.19 or 5.20, like just do something close to it. It's not going to be exactly the right answer because we have to round. 2 sine e to the x divided by 4 plus 1. Oh no, I am not putting this in the right place. Sorry, guys. Well, I'm just going to go back up to this function because we already used this one. I'm just changing this bound that I had already used. Oh, I'm doing such a terrible job right now. I'm so sorry. Okay, I need to press delete, not clear. Delete. Okay, 5.19. That equals 12.37. And then I'll add that to 2. 12.37. And so my final answer is 14.37. And that is our answer. So thanks for hanging in there. Hope you have fun. Bye.